The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Right, so our next speaker is Doug Hooton from the University of Toronto. And Doug really doesn't need much of an introduction. I think if most people know him, but he was one of the only 2 people who actually responded to my request to provide me a bio. So as long as he did that, I'm going to read it. Doug is the National Sciences and Engineering Research Council Association of Canada Industrial Research Chair in Concrete Durability and Sustainability at the University of Toronto. He's got a long experience in concrete durability and materials issues. He's a fellow of the American Concrete Institute and of ASTM and has received numerous awards. And coming up here this year, he's going to be inducted as a fellow of the Canadian Academy of Engineering. So we look forward to Doug's presentation here to discuss international trends in beneficial use.
Yeah, good afternoon. So I was asked to speak about international trends. I was given the topic. So being from Canada, I guess that qualifies me for being international, even though I had to fly north to get here. And apparently they still have snow here. But I'll do that. And since this is on our Dick, I had the opportunity again with Larry to go fishing with Dick down in the Florida Keys a few years ago. That's with the marlin there. But anyway, we had a great time with Dick fishing, and he's showing how big his fish there is there too as well. So it was a fun time. So missed Dick, done a lot of stuff. And then Dick was the one, again, responsible for creating the C-130 committee on sustainability at ACR. It was one of Dick's big pushes to get that in play and move that forward. We'll talk a bit about Canada, because being from Canada, I probably have more to say about Canadian ash use than other places. It's around 28, I think Tom, you indicated 43%, but Canada, at least with the latest data I have access to, is about 28% overall. In Canada, similar to the Ash Association, we have a Canadian Association of Canadian Industries Recycling Coal Ash, CIRCA, and they are involved with promoting the use of beneficial use of ash as well. That's the latest government statistics in very fine print. That's what I can put together quickly. And so on fly ash, it produced about 4.3 million tons, of which it's about 1.2 million tons has been utilized. This is from data averaged over 3 years, 2009 to 2011. So it's about 28% on the ash. The desulfurization gypsum, though, is 100% utilization. So that's one of the products that's been picked up quite readily by industry from the CCPs. And the Environment Canada, which does the regulatory work similar to the EPA in the U.S., continues to maintain that coal-combustion products are non-hazardous. And we keep going back to what he circuited us to ask them that question and keep saying the same thing. There's no plans to move it. However, if EPA ever did declare it hazardous, you can see what's going to happen in a very short time. We've already seen that in the east coast of Canada, where people in Newfoundland were getting fly ash from Nova Scotia from one of the power plants there to control alkali silica reaction, because Newfoundland is just basically reactive aggregates, the whole province. They were using fly ash, and all of a sudden they couldn't get fly ash because the Nova Scotia Power Company said, we're worried about what the EPA is going to do, and that's going to open up our liability, even though it's in a different country. So they stopped supplying fly ash. So now the concrete company still makes concrete with reactive aggregate without fly ash. with grade. And of course, there are challenges to these. Since 2012, they've required powder activated coal. They've required mercury reduction abatement. That's largely affected the big coal plants in Alberta and Saskatchewan. And they're using powder activated carbons to scrub the mercury. And this has impacted the ability to intertrade concrete. It's not so much, there is some LOI increase, but it's the activity of these carbons. It's very high activity carbons, so that then it sorts some of these organic admixtures. I understand in Alberta they're experimenting with some new materials that will scrub the mercury with much less impact on that. But the initial materials had some impact on the air ability to intertrade concrete. I don't have any specifics on that because it's proprietary. In terms of Canadian specifications for ash, they're different than the ASTM/ASHTO specs, is that we classify the ashes based on the calcium content rather than the sum of the oxides, the sum of the silica, alumina, and iron approach. And I guess the sum of the oxides was meant to represent the glass phase of the fly ash. Well, I'm not sure why iron was ever in that story, because most iron in fly ash is this magnetite or ferrite individual particles, so it's not part of it. And even some the silica and the alumina, some of it's there as mullite, inert ceramic material essentially. I've never quite understood why the sum of the oxides is a smart thing to do, except it was probably easier to measure the calcium at the time using chemical techniques. And the other thing about the Canadian spec is that fly ash is part of the cementitious system. At ASTM, fly ash specs 618 is in the C9 book, the book of concrete, which is the concrete spec. It's not under the cementitious materials part. Ours used to be like that, but about 15 years ago we picked up all the materials, fly ash, slag, silica fume, natural positive, we hauled them all in and put them under one big standard for cementitious materials, because it's part of the cementitious matrix in concrete. Then we actually fit everything into one standard. We have Portland cements, blended cements, and all the supplementary cementing materials in one standard, A3001. And it makes it a lot easier to deal with the cementitious system, having that sort of logic to it. And of course, part of this, the reason it's still in C9 and ASTM is history. When the fly ash people, partners, came to ASTM way back in the 50s, the cement people didn't want anything to do with them. So they went over to concrete because they gave them a home. And that history goes back a long way. And it was the same in Canada. And it took we had to fight to move those things into the cement standard because of that history. People have long memories. But it makes a lot of sense that it was part of the matrix, the cementitious matrix. So we have these classifications which we've shifted a bit. The Class F ashes, instead of being 70% or more some of the oxides, it's up to 15% calcium oxide. So it basically accommodates the Class F ashes that you would see here as well. And then we have two types of C ashes, 15 to 20% calcium and above 20%. As we see the really high calcium ashes are ones that have some severe challenges in terms of some of the durability concerns, like sulfate attack or alkali silica reaction mitigation. And the ones in between, the CI ashes can often perform very well. Not always, so we need to be tested. So we require testing of the CI ashes. Well, we require testing of all ashes, but the CIs can be either really good or sometimes they behave more like a CH. But once they get about 20% calcium, then we have concerns about the durability issues. They're often good technical ashes, good early setting times, good strength development, but they often are associated with some durability issues. We also sort, in terms of ASR, on alkali content, the equivalent alkali content. We consider anything up to 3% alkali as being low in terms of the ash. And then we have a second category, if you're up to 4.5%, you need more mitigation in terms of mitigating the ASR potential. And if it's above 4.5, you have to use testing rather than an expert system to prove it. Okay, so E3001, what was I going to show you here? Oh yeah, there's the calcium. The top line there, the F ash, CI, and CH, it's all regulated based on the calcium content of the ash. And then we combine some natural pollutants, just like the US F, CI, CH, and we've got slag, silica fume, and we've got a lower SiO2 silica fume as well. They're all in one table in the standard. And so the only thing that applies to ash, really other than sulfur trioxide and loss of emission, is calcium. Okay. So in terms of how that relates, as I said before, this is some of Mike Thomas's data that he's pulled together, comparing how you would classify things in ASTM on some of the oxides versus calcium oxide. And the 70% some of the oxides is around, if you draw through the median, the best fit line's on 17%. But when you get down to, the noise in the data, it's about 15%. So in terms of performance, I'm pretty comfortable with the 15% being similar. So an F ash on one side of the border is pretty much an F ash on the other side of the border. Okay. Now I mentioned about the calcium content. This is ASR expansions now. But this is a plot again. This is some work by Mike Thomas at MedHatch plus some other data put together. This is concrete prism expansions at 2 years. We typically use 0.04 as the failure criteria. So these are different types of fly ashes and different 25% fly ash, high alkali cement, but different fly ashes. And from different studies. And what you see is that up to about maybe 20% calcium ashes, you can get good performance with 25% ash, replacing high alkali Portland cement with reactive aggregate. And then above that, you start to see this big shift. And then there are cases you've got a really high alkali content in the ash. These ones are all over 5% equivalent alkali. But you can, even at a lower calcium, you can have some issues, which is why we have the secondary limit on the alkali in the ash. So the calcium content seems to relate to the ASR control, and it makes sense because you're trying to change the hydroxyline pore solution concentration. To mitigate ASR, you've got to reduce the pore solution concentration of hydroxylines down to a level that they won't attack the siliceous aggregates. And so if you have high calcium fly ashes, you're adding phases into the system that can keep that hydroxyline concentration up, unless you put a lot of fly ashes. But at 25%, it's insufficient when you get to these high calcium ashes. So it's not that you can't use them, you'd have to use a lot more fly ash in that case to control it. Okay, now in sulfate resistance is a similar graph. This is with some ashes where we blended different F's and C's, or this is Mike Thomas's data again, because I was scrambling to get some data together here. Again, related to calcium content. Typically we want 0.1% expansion or less in C1012 at a year. And so those, when we get down below that, if we're down below 20% calcium content in the fly ash at a 25% replacement level, we've below that expansion limit. And if you want to be sure, we just get a little more safety factor in 15 is what we pick. So we're saying 15 to 20 may work, but you need to be more careful in the testing, and then below 15, at a reasonable level, you get good sulfate resistance. But you start to see the sulfate resistance deteriorate at a given amount of ash, because you've got things like tricalcium aluminate in some of these high calcium ashes. You've got other phases in there that may contribute to the sulfate reduction. It may make it actually be detrimental at a given level of ash replacement. So the calcium content is where we are in the Canadian standard with respect to those two durability issues. And that's why we picked calcium as the indicator. The other thing, since I'm talking about random elements related to fly ash, we use the same strength activity test in the CSA as the ASTM 311 test, and we had the same test limits as in 618. But then we made them optional because the current test method in 311 and the current limit in 618 means you can take inert fillers and pass the test. So why bother doing the test? And so we just said, look, it's optional. We're not going to mandate anybody doing that test because it doesn't tell us anything. Until somebody comes up with a better pozzolanic test or a better test limit to evaluate it in comparison to. And so when you look at the table for supplementary materials, the only test that it requires for a silica fume, the rest of it's non-mandatory in any of the fly ash categories. And there's the optional test, and again, it's the same thing. It was the 28-day test, just like in 311. with the 75% requirement, when you take 25% of the cement out, and so essentially you get 75% of the strength after 28 days. That's great. So you can take a ground quartz filler and pass that test. The limit's in 618. You can take a ground limestone filler and pass that test. So to me, the standards committee at ASTM needs to think about that in terms of modifying the test. We did some testing. I did some testing together with Larry Sutter a few years ago on a pool fund study, and here's we used a quartz filler in this case. We used it with 3 different Portland cements, and we tested it relative to 8 different fly ashes, C's and F's, and we looked at the strength activity index, and this is just with the quartz filler. So here's with 3 different Portland cements of different alkali content, C3A, 7-day strength, 28-day strength. There's with the filler, so that is the strength activity index in Ashwin 295, which is the same as 618. So we passed the test at 7 and 28 days with 25% ground quartz, which is what you're asked to test it at now, 25% ash. So it's really not giving us anything. Now, if you went to 35% replacement, which is the old activity index test, then those fillers wouldn't pass. Because 25% is about optimum for a lot of different fillers. But when you get up higher replacement levels, when there's nothing going on there, then you start to distinguish the non-reactive materials from reactive materials. So one of the big problems was that switch from 35% to 25%, which is about 15 years ago or more. And so they wouldn't have passed the old strength activity index under the old system. Okay. We tried just for fun. We did it with 3 different fillers, and we got different results. Some fillers work better than others, but you couldn't distinguish the fillers from some of the fly ashes in that case, especially the 7-day test. Okay. Now, closer to home in Ontario, and Tom mentioned that Ontario is getting out of the fly ash or the coal power production business. By 2014, all the coal plants would be closed in Ontario. They were shutting them down over the last 7 or 8 years, several units at a time. And it used to be that coal power was our largest generation in Ontario back when I was with the power company. So, but for the last 25 years, the ash that has been used, because it was used for peak power production, it tends at variable and high loss and emission values. We often see loss and emissions 12, 15%. So which didn't make it very useful for concrete, but it has been used very successfully, almost 100% of the Ontario ash, as cement kiln feed by the cement industry. If you take a material that's got 12, 15% fuel in it, they're getting free fuel with the raw material. They get their iron, their silica, and their alumina from that material, and the silica is already fused into a glass, which makes it easier to combine in a cement kiln. They actually saved about 15% of their energy by using fly ash as a raw material and as a cement kiln material. So they've had unit trains running into Michigan. Alpena, Michigan is converting Ontario fly ash as part of their raw mix for the last 20 years or so, amongst other companies. And it's the cement companies that are largely using the FGD sludges as well as chip replacements. Okay. So I mentioned this, they're shutting down, the last units will close down in 2014, except some, they're going to convert 1 or 2 up in northwestern Ontario to convert biofuels because of local employment issues. So there's politics involved with all this as well. Now the tobacco farmers in southwestern Ontario are wondering why they can't burn tobacco instead of coal and cement kilns. Okay. So I thought I'd talk about a couple of examples. How am I put my time on? Yep. I'm good? Okay. A couple of beneficial, on the beneficial side, I'll just talk about a couple of things since I'm in Ontario about where ash has been used positively. This is a dam that was built in 1970 up in northern Ontario. There's a spillway on the left and the penstocks coming down, and the main front of the dam is concrete, the rest is rock fill. But it was built with reactive aggregate. Because that forebay up above the thing, the dam had to be excavated. It's all reactive rock. And of course, it's way out there. This is about 6 hours north of Toronto, and they had to use it. And at the time, there wasn't a lot of options. So it was built with this reactive gray white, the argillite aggregate. They only had the 227 prism test then, and they found with that 227 testing that you could control this with low alkali cement, or you could control it with 20 or 30% glass F ash. And they gave the contractor the choice of which to use. And it turns out the low alkali cement generally was difficult to obtain, more expensive, so they ended up bringing in by train loads the fly ash, and used high alkali cement in that project. There's the arrow showing where it is. Goes in as a map of Ontario with reactive rock types. So Toronto's down lower. And we're hidden under where it says USA somewhere. This is just some information on the rock types, not really important. But they identified these reactive phases in the rock types that were used. And that's the original 227 data, showing that if you made it with high alkali or normal Portland cement and this rock material with a dam nearby that was built at a similar time, then they would get deleterious expansions if they could either use fly ash or low alkali cement that they could control that. And then later on we were able to get some aggregates because they were crushing the rock. There's still aggregate stockpiles of all the different sizes up there. And Mike Thomas remade some concrete prisms, and it shows that with the normal high alkali Portland cements, you would get deleterious expansion. You'd exceed 0.04 a year. And with the same cement and the 25% fly ash or the low alkali cement, you can control that aggregate. So there's been more Fournier digging aggregates. We've been up there several times. As you can go back, it's great because not only have you got the dam to look at, you can go get the aggregates and do more testing. And it just shows that in a dam, this is just a cross-section to where the gate structure is in the spillway section, that there's different types of concrete that are used there. And I know it's a difficult slide to see, but there's core concrete with up to 3-inch aggregate in it. There's other concrete with 1.5 inch aggregate. They got face concrete on the decks where we're exposed to frost with 3/4 inch aggregate. And the highest strength there is 4,000 psi at 28 days, but most of it's like 2,000 to 3,000 psi at 28 days or 90 days even. So the core concrete, because they're looking at mass concrete and very well heat hydration, they don't want to have thermal cracking. So they're relatively low cement contents, low strength. But this thing is now 40 years old. We were up there in 2010 when it was 40 years old, so now 43, I guess. And there's no evidence of ASR damage in the structure, made with a 1.1% alkali cement, but 20% F ash, and this reactive rock. So here's just on the upstream on some of the intake structures, and there's no damage. This is on one of the wing wall sections. Again, there's no ASR damage. There's a bit of frost damage in a couple of places, but no evidence of ASR. We were down in the tunnels. We've taken cores. We've done damage rating indices. We're not seeing any evidence of damage with that structure. Yet there are structures built with similar aggregates in the neighborhood with Portland cement that have all cracked up. So we've got a good basis for that. So some of the cores we use for the damage rating index testing, we've got cores in 6 feet into the structure to evaluate the performance. Now, related to this, or similar thing, Mike Thomas has been looking at a structure out in New Brunswick where they've got a dam there that needs to be replaced because of alkali silica reaction. They're planning to do it about 15 years from now. But one of the interesting things there, which relates to what Tom said, is that they may not have the power plants that are producing coal ash there now, may not be in operation in 15 years. So they've got landfill deposits, and they've actually excavated some of the landfill ash and used it to evaluate its performance to control ASR. If they need to rebuild this dam, because they're likely going to have to use the same reactive aggregate because of the volumes and the locality. So in 2010, they passed 10-foot cubes with this material. In addition to the normal lab testing in small cubes, they passed 10-foot cubes with these with both reclaimed and new ash. That just shows the dam there. It was built in the mid-60s. It started to show damage in the about 10 years later. I was out there around 1982, I remember, and they were having to post tension in it so the dam didn't break in two. And the turbines stopped working for a while, and they put 7 diamond wire saw cuts through it. Over there's 15 millimeter saw cuts, and within 24 hours they're closed. That's how quickly the stress relief occurs. And they've been spending a lot of money on that using a high alkali cement in the 60s. They ignored the advice of the petrographer that maybe they should look for low alkali cement. And they paid for that. So anyway, they did some mixes for the demo. They did high cement content, boosted the alkalis, but looked at ash 30, 40, and 50% to see if they're going to build this new replacement dam, that whether it'll work or not. And Mike did work on the Mortar bar test, the concrete prism testing. Got smaller exposure blocks outside, and they got these big 10-foot blocks out there, which were casted. So they'll almost have 20 years on the blocks by the time they need to pick the aggregate. That shows the blocks outside. And it shows the expansion after 3 years. It shows that they've already reached failure expansions on the control blocks without fly ash after 3 years in the field. But with the process or the reclaimed ash, they're not getting expansions. So they're looking at potentially using the reclaimed ash to those big blocks to rebuild the stand. Okay. 2 minutes? Okay, I'll just mention Europe briefly. A couple of things. In Europe, fly ash largely is covered under the blended cement specs. There is some ash available that's added to concrete, but a lot of it's used under these cement specs, typically the CEM2As, and V stands for the siliceous class F ashes, and W stands for the calcareous or high-line fly ashes. There are some other categories where they use fly ash, but EN450 has these different levels of ash, used up to 20% or up to 35%, and differentiated on the type of ash. It's interesting, the strength activity EN206, which is their concrete spec, there's also a standard EN450 for fly ash. Their strength activity test is pretty similar to the ASTM test. They take out 25% of the cement, put in 25% ash, and in 28 days, you've got to have 25% of your strength, 75% of your strength. So, in other words, you can do nothing and still pass. But the other interesting, and I didn't mention this earlier with the CSA standard allows co-combustion of up to 25% pet coke with the coal ash, because a lot of plants are burning pet coke in combination with ash, so we actually allow it in the spec. I think the ASTM 618 is a little quiet on the situation. But EN450 allows co-combustion as well in their standard, at least the latest version. They limit the amount of co-combustion material to about 30% of the ash composition. But this just shows what they mean by co-combustion. Solid biofuels, which could be wood residues, could be animal meat, could be municipal sewage sludge, could be paper sludge, could be pet coke, or it could be some solvents. So when they say co-combustion, it can be a whole host of things that are allowed under the ash spec in Europe. So that was just a bit different. One of the things I got out of the Japanese stand, actually is a report that Professor Nagataki wrote some 10, 12 years ago. They have a requirement that the SiO2 content of the ash, regardless of the type of ash, has to be at least 45%, which I thought was interesting. And then when you use it in concrete, you take the LOI of the fly ash you use to establish your mix designs, and it's not allowed to vary by more than, about 1% either way if you're doing reproportioning during a job. And that's why they control the LOI of the ash. You establish a base LOI, and then you have to stay within the limits of that. So I thought it was an interesting way they approached that problem. Okay, so in summary, coal fly ash is changing because of the environmental regulations. Coal combustion is becoming more common. The powder activated carbon issue for mercury control is becoming a bigger issue. The current standards, at least here and in Canada, don't distinguish ash from fillers, and that's an issue. And the calcium oxide content, I think, has a more direct link to some of the durability issues that we're concerned with use of ash in concrete. And I think the standards need to adapt to those changes if they want to remain relevant in the marketplace. So I'll leave it with that. Thank you.
Any questions for Doug?
When it comes to mitigation of ASR, it looks like the depth ash is the ash of choice. Do you guys ever use Class C ash from Canada for mitigating the ASR? And why is it that you really have to boost the addition so much?
Well, again, with ASR, you're trying to reduce the hydroxyl concentration in the pore solution. And ash does that by reacting with some of the alkali and the calcium to reduce that hydroxyl. And you're not reducing it really low. You're drinking it down to about, if you get your pH down around 13.2, still alkaline enough to prevent corrosion, but it basically makes the concentration of alkalis in solution below the value that it will cause attack the aggregates. And so with the Class C ash that has calcium in it, you're not going to have that same reduction of alkalinity in the pore solution at a given amount of ash. So instead of using 25%, you might have to use 40%. Because more of it will react, and eventually you'll get reduction in the alkalinity of the pore solution.
Okay, thanks.